thank you for coming to this talk. So what I plan to talk today is some development in this attempt to bring a categorical interpretation of the GKZ D-module. Maybe what I should say is that, and I will explain this today, the importance of the GKZ module in mirror symmetry is basically the fact that it provides a powerful tool for checking things out in the examples that come from toric geometry. So mirror symmetry, of course, is not toric in nature, but initially, the initial conjectures were made in the toric case, and then the sort of for any kind of new idea that people have, it's always been the case that the first attempts to prove a certain statement were done in the toric case. So, which brings me to the today's talk. So what I want to explain is sort of the a conjecture made in physics, well, in physics, physics and math, by in a paper on the archive. I'm not sure if they published it, but by Aspinwall-Plesser-Wang. So this is maybe, I think that's the only paper that is that's the only paper of this triple of authors. So it's on the archive. What is what basically what they do there, they propose a mechanism for dealing in the toric case with this, with what in physics they call the massless brains. And as it turns out, this sort of idea fits rather nicely with this point of view that's been around now for a couple of years, maybe 5-6 years, by promoted by Kapranov and Kontsevich, and I guess it started with the ideas of Kontsevich about on Fukaya side, and then it got expanded on this others, on the B side, what I would call the B side, by Kapranov and Sheckman, and then there is more to it. So I should also mention, before I get into the details, there is a recent paper, maybe a month ago, by Vandenberg and Spenko, which has the title something like the categorification of the GKZ D-module, which is rather scary. So you think that there's nothing else for me to say, but their construction works in what they call the quasi-symmetric toric case, which for those of you that saw my previous talks about this, I talked about this in the context of what I would call in toric geometry, the Lorentz construction. They don't use this terminology. So I mentioned this special case because what's special about it is that the characteristic cycle, the discriminant locus, is rather special. It's rather nice. So one could really write down algebraically things very explicitly. So so anyway, but my point of view is a little more, would be a little more general than this quasi-symmetric case. And as I said, the first step would be to try to understand the toric case. And I will not be able to go as far as Van den Berg and Spenko. They really have a algebraic, I didn't read all the details of the paper, they really have an algebraic construction that seems to give the Schober, really, which I'm not able to do it here for many reasons. But the main technical reason is that the discriminant locus, or the characteristic cycle in general, is much more complicated than in this quasi-symmetric case. So, all right. So, so what I want to do then, as I said, my plan is to just update you kind of on the techniques that are used here, and then explain the conjecture and kind of the sort of the idea about how this might work, and how the technical details fit in the general picture. So let me present quickly the combinatorial context of toric mirror symmetry. Perhaps I shouldn't even do it here with this audience, but I'll still do it just to fix the notation. So we have A, the famous A, a finite set consisting of, say, n vectors now living in a lattice. And I will assume that for today's talk, for many technical reasons, it's good to assume that there exists what I would call a degree function. So in other words, all the vectors lie in a hyperplane. P, let's call it P, I think the convex hull of this polytope. So, so the usual picture that one sees here is you have this hyperplane, and the polytope, and then one builds this cone. So, so the in order to get geometry, one needs to consider some triangulation or a fan. So let sigma be a simplicial fan whose rays, so one-dimensional vectors, are generated by the VIs. In fact, I'm a little sloppy here. So the fan, it only needs to, technically, it only needs to have the property that it's a cone, it's convex hull of all the cones, the union of the cones in the fan is the big cone. So as I said, to fix notation, let's call X sigma the toric, the Lee-Mumford stack associated to this fan. So the hyperplane condition that the hyperplane condition guarantees that implies that X sigma has a trivial canonical bundle, trivial canonical class. And so, we call it a local Calabi-Yau, or Calabi-Yau for the purposes of this talk. So just to, the geometric meaning of taking such a fan is that, as it turns out, X sigma is Gorenstein resolution of the Gorenstein singularity, which is spec obtained by, that's kind of the yoga of this toric machinery, of the spec of the dual cone intersected with a dual lattice. So N is the dual lattice. So, and so we're talking about, as I said, the toric birational geometry essentially, and for any complex function, say I don't know, from A to C, we can define some the hypersurface XF, I guess that's which is the proj of C of sigma over this F, where F is the hypersurface of the form something like AI x to the VI. And so XF is, so XF is now a projective Calabi-Yau, and it gives the mirror picture. The mirror picture. So I'm kind of skipping here a few details, but I'm sure, namely, one needs to look at the X sigma, take a Calabi-Yau inside X sigma to a projective Calabi-Yau, and that's going to be the mirror of this XF, really. So that's how we know this works. So now, again, for those of you who, I'm sure everybody heard this at least a few times. So what Batarev noticed is that the periods associated to the variation of complex structures on XF are solutions to the GKZ D-module associated to this combinatorial picture, associated to A, I should say, and with this observation, I guess the lots of applications have opened up from all points of view. And I should say that one, perhaps this is a good moment to say this, that of course what this talk a priori is about homological mirror symmetry, but what we're doing here really is kind of do sort of a simplification or a skimming of homological mirror symmetry in order to not to have to discuss about the Fukaya side. So of course one could do that, but I will the point of trying to check some consistency conditions is to use this machinery invented by Gelfand, Kapranov, and Zelevinsky. So let me write now quickly the system that described that this is. So it's a system on sort of strange. So the way I'm going to write it, especially, so it's the number of parameters. Actually, I think I call them A's, if I remember. Yeah, so there should be A here, A1, AN. So this V is an integer point in the cone. So this GKZ basically now it looks like it's on infinite. A solution is an infinite set of functions, but beta is a parameter, important, although kind of hard to grasp if you have never seen this. The importance of this is hard to grasp if you never worked with these, so I'll try to talk a little bit about it. But so the equations look like this. So if you take the derivative of so taking one derivative moves you sort of deeper in the cone by the vector vi, and then the what's called the homogeneity properties, something like this. This is the system, and one can prove then that it reduces to a finite. It turns out that it looks, as I said, very infinite, in fact, but it looks like it turns out that it reduces to a finite number of PDEs on a finite number of functions. So it really is a finite dimensional for all intents and purposes. And the version I wrote here is not quite what the GKZ wrote down. So this is kind of a version that I'm popularizing when I give this type of talk. So it's basically is Lev's idea to improve, so to speak, the usual GKZ. In what sense? In the sense that in the so-called good cases, which I don't want to discuss now, this reduces then BBGKZ, as we called it. The better behaved GKZ is the same as the GKZ. So that good cases means basically that the set A is normal. So the associated, there's some normality condition in that definition that is needed for the GKZ to have properties. Otherwise, the problem is that the sheaf of solutions has the wrong dimension, which is, from the point of view of mirror symmetry, is a big problem, in fact, because we know what dimensions we expect. So is doing is cutting down on the number of solutions. So this, as it turns out, this BBGKZ has the right number of solutions in all cases. So so the BB GKZ has the expected number of solutions of periods, which should be exactly the dimension of the space of periods. So all these, the ones that the so-called bad ones are ignored. So this is, of course, looks like a small thing. On the other hand, if we try to do trying to do any kind of functorial calculations with the usual GKZs, it causes all sorts of problems. So I should say a remark here that again is very important for the calculations, but I will not be able to do justice. But let me just mention it, that in fact the BBGKZs can be defined in a very general context. So in fact, if I take some S, say a set in the cone, which is, say, so the only property needed is closed under addition by VIs. So as long as adding VIs doesn't get you out of the set, you can actually write down exactly the same definition. And now instead of having V in the full cone, you can have V in this set, and then you so you would have some so not very surprising. This of course has to do, the geometrical translation of this is about something to do with support of the sheaves that we're going to talk about. So the notation would, I guess we can write something like a GKZ of, I don't know, A S beta. So this would be the D-module associated to A, S, and beta. So if S is the full cone, then we're back to the usual definition. So the physics statement is that and that's the physics statement exploited by, in this paper by that I mentioned, by Aspinwall-Wang and Aspinwall-Plesser-Wang. The physics statement is that the quantum corrected Taylor space of some Calabi-Yau should be of some X, I'm going to be sloppy here, is isomorphic to the moduli space of complex structures on X, say check X mirror. So there have been lots of attempts to kind of define what this means mathematically. Of course, the most famous one is Bridgeland's definition, also inspired by a physics idea, some physics ideas of Douglas and Aspinwall in Douglas. So in other words, we should think about this as some kind of space of stability conditions. So this is, I guess, I see lots of paper now. This is called the stringy moduli space. So when they mention stringy moduli space, that's what they talk about. And as I said, in Bridgeland's definition, an essential ingredient is the central charge for which is a function from K0 C. And as it turns out, from our point of view, the Z should be a solution to the GKZ system. So that's kind of the connection with, as I said, with the classical mirror symmetry picture, the connection with the more recent Bridgeland stability conditions, and then the goal then would be to, as I said, my goal at least, is to use this machinery of the GKZ D-module to understand the birational geometry on the B side, including, and this is kind of the purpose of giving this talk, including the behavior at the discriminant locus. So from the point of view of, so just to recap a little bit, so as I said, we're talking about classical mirror symmetry. So you write down, say, a hypersurface, I think I called F, and you look at the discriminant, the classical discriminant. As it turns out, this machinery does, it adds a few more very interesting components to the classical component of the discriminant locus, corresponding to the faces of the polytope, the convex hull of the set A, and that turns out to be intimately connected to be, in fact, this new discriminant. So I think Gelfand, Kapanov, Zelevinsky call it the A determinant. That one is turns out to give on the nose the characteristic cycle of this GKZ module up to the corresponding multiplicity. So all of a sudden, as I said, we have on one hand components of the discriminant locus in the complex moduli space, and on the other hand, we have the characteristic cycle for functions like this, like the central charge, so which also have singularities along these components. So that's kind of, from my point of view, this is kind of the way I see this duality between the two sides. So there is one more important ingredient that I have to mention. The tool, the crucial tool for this in this story is what I would call is the topological mirror symmetry map, which is I'll call it MS. So it goes from the dual of, say, the K group of to the solutions to GKZ, what I called, I guess, A sigma beta. So so how does this works. So this, of course, in its classical version of it is something that goes back to Giventhal. And it's still, as far as I know, at least, the only way to really connect the two parameter spaces. Of course, this is essentially, this provides the mirror map. So, but it in a way which is highly transcendental, as expected. But this is kind of a direct. The advantage of this approach is that it gives a direct connection to the between the two sides. So so maybe I should say one word about this. So what is this? So I don't want to maybe, so this is the deformed so this is the deformed Grothendieck ring of the stack of the stack. So we're talking about coherent sheaves, of course, X sigma. So the non-classical thing here is that there is a deformation parameter having to do with this beta, and if beta is 0, then we get the usual classical K group. So let me maybe, so how is this defined? Since this might be interesting, and I don't think is that well known. So this is proven in, I think, in a paper, kind of old now. So but it's basically is the quotient. So this is the quotient of, I'll work over C, of course, of R1 plus by the relations, the following relations, that the product of 1 minus Ri is 0 if if I, the included in 1n, does not generate a cone in the fan. And then the presence of beta is that if you take, say, instead of getting 1, as you would get if beta equals 0, you get 2 pi, I guess let me write it, -1 h of beta for any h from m to z. So as I said, if beta equals 0, then we just get k0. So, and so this, as I said, it's a downgrade of mirror symmetry. So we're downgrading at various levels. So now we downgrade it from the derived category of, say, even of this dilemma for stack. We're downgrading it to the K theory. But finally, now we have, as I said, the direct connection here, this topological mirror symmetry map. And just to write you how nice or ugly these gamma series look. So the way it looks, it's something like this. Of course, I'm not going to insist on this. This is so. But it's kind of, as I said, very natural. So it's Li plus 1 over log. So that's where the gamma function comes in. So indeed, it's a gamma function. So in that respect, it has the great feature that it covers a lot of the classical hypergeometric series that are known. So so in the story, as I said, there is some something more that has to be said. So right in the beginning, I mentioned the fact that this the GKZ can be, this better behave, our version of the GKZ can be generalized to cover also the case of sheaves which certain support in the stack. And the case that I want to mention is this the case when I'll call it, I know how to call K, maybe K C, but it's a little misleading, X sigma beta to solutions to GKZ to A sigma interior beta. So so these are basically solutions to the GKZ functions when instead of taking considering functions at all the points in the cone, you just take functions at the points in the cone which are inside in the interior of the big cone. So this, as it turns out, is the Grothendieck group of the coherent sheaves in X sigma, which are supported on the exceptional locus, which correspond to this, as I wrote in the beginning, of this Gorenstein resolution. So this was spec of C of C dual. And not only that, but you can really mimic the pairing, the natural pairing that you have between, say, KC. So this is something with compact support. Into C. So there is a way of conjecturally mirror, and you have a pairing on solutions to GKZ A sigma 0 beta, solutions of GKZ A sigma beta. And writing down this pairing is kind of a little challenging, but it seems that there are examples when, again, it really works on the nose. So just, so I mentioned already that the discriminant we're discussing is sort of, I think it's called the A determinant, if I'm not mistaken. And it's EA. So it's a product for each face, gamma face of the convex hull of A. So it's the classical discriminant with some multiplicity, which actually in the BBGKZ, in some cases of the BBGKZ D-module, the multiplicities are different from the ones in the GKZ module. And this is what I wrote here is this is the classical discriminant associated to a polynomial whose Newton polynomial is now not the full set A, but is the intersection of the set A with the faces of the big cone. So basically what GKZ proved is that there are more components, as I promised, and they are all under control, and they're associated to the as I said, to the faces of the big cone. So so the proposal then so this is kind of how Aspinwall-Plesser-Wang stated it, is that for every face gamma, there exists a spherical functor I'm not going to go now through the definition of a spherical functor here. There exists a spherical functor from a category, let's call, I think they call it Z of gamma into dB of x. And let's call this functor S gamma, maybe. So S gamma, sorry, no, I don't want to call this one. So for every, there exists a spherical functor where Z of gamma is defined by the cones in what I call the star of gamma. So in the following way that the fan of Z of gamma is the projection onto the quotient of the lattice M by Z by the I can, to make it, perhaps I should maybe make it over C just to avoid here at this point any torsion issue. So let's say M so what one does, you take the face and you project onto this quotient, and then the fan is the projection onto of the cones in star of gamma, sorry, which consists of all the cones of sigma that have a face in the interior of the cone generated by sigma in M. So as I said, we're talking about a polyhedral cone. We're taking a face. We're taking the star definition here is not quite the one that you would find in the toric geometry books. There is some relationship between this one. So this one, from a birational geometric point of view, is kind of the toric variety that we get is birational equivalent to the one that is discussed in the toric geometry books. But so one could think about this so maybe I should write here dB of, so one could think about this story as the usual diagram that you have when you talk about what I would call spherical functor. So this is dB of, or easy spherical functor, sorry. So this is what I would call Q. This is what I would call Q. Sorry. What I meant is, so I guess I'm going to write the same thing, but without the maps. That's what I meant. So dB of E gamma is the image of the spherical functor image category of the spherical functor in dB in dBx of x. So that's a proposal. It's actually quite explicit, and what is not very, and I'll try to, the minutes I have, I'll try to do a little example, but the way the proposal was made by Aspinwall-Plesser-Wang, they actually noticed there that there is a problem with their proposal in the sense that moving along a component of the discriminant locus, this this spherical functor might change. So the origin category does not change, but the actual functor itself, the spherical functor, might change. And this has to do with the fact that, in fact, the way this should be thought of, so observation or remark, one gets such a spherical functor for each stratum in a Whitney stratification of the zero set of the GKZ A determinant. So in other words, the spherical functor are associated with the interior of with the open strata of this stratification. So, so maybe I'll. So let me then before as I said, I want to do at least one example. So the B-brain category associated to such strata such a strata, a stratum rather, is then obtained. So if I call my spherical functor S gamma, there is a natural transformation which we don't have. I obtains as the Seidel localization of dV of x with respect to the natural transformation the one written here. So I should mention here, I believe, although I've only seen indirect evidence, but I believe this proposal is also consistent with a proposal that, as I said, I've seen in talks by other people, but they attributed to Denis Auroux. That's kind of what Denis is proposing, I assume, for the what they call the singular, the category of the singular fiber, and I think, of course, they're interested in the Fukaya side too in that context. So, so there are two extreme cases here. One is when the face is actually a one-dimensional cone. So it's actually, we're talking about a vertex. And in that case, where the associated spherical functor is, this is a well-known story. So it's kind of, sorry. So D is an associated divisor. And then the associated spherical functor, spherical, is twisting by this line bundle. And I guess this category, the B-brain category, X, I know, I guess I didn't give it a name, so would be the category of sheaves on the open part of the of this X on the complement of the divisor. So the other extreme case is when so we're taking the full polytope, so to speak, and then the spherical functor that is corresponds to the actual resolution. So so this is going to be the image. So where the image of dP is the exceptional locus. So I don't know how to call it E. Let's call it E, and then this B-brane category in this case is going to be dB quotient by the category generated by O. Yes, I have the structure sheaf of this. So let me. I had some examples here, but let me. I have a few minutes, so let me discuss maybe. Let's take the following toric situation: the total space of the anti-canonical bundle of the Hirzebruch F2. So so the fan, the vectors or something like this. So this is the origin. So this would be V0, V1, V2, V3, V4. So V0 would be 0, 0, 1, V1, 1, 0, 1, V2, 0, 1, 1, V3, minus 1, 2, 1, and V4, 0, negative 1, 1. So this in the language, this would, sorry, this is the set A. And the convex hull of these, it's the important thing is there is one face here whose which contains where there, for which there is an affine relation, and so this, from the by rationality point of view, there are 4 ways to triangulate this. So maybe I'll try my best quickly to these are the big cones, or I guess I could have done this with colors, but I'm not, that would take me a long time. So so the interesting thing, for example, if we look at the face as a one-dimensional face, say, let's say that we look at this point in all the, we see this phenomenon that I already discussed, that the star in the first case would be would consist of these 2 cones, but in the last case would consist, so this would be V4, V3, V4, V3. This is V0, which certainly give different categories. But again, as I mentioned, this is kind of, would be the generic part of the stratum. well, this one would be a deeper strata in the discriminant. And the same phenomenon appears if we deal with one. The only interesting face, as I said, is this one that contains, so it has 3 points. And I have to be careful here. So I guess in this, and then, so this is V0. And so we again see the same phenomenon, and this is kind of the generic spherical functor associated with the stratum, and then there for each of in each case, I guess sometimes these coincide if we do this explicitly, but there will be some deeper stratum, the discriminant. So I'll say one more thing, and then I'll stop. So the machinery of the BBGKZ that I mentioned earlier has this big advantage that it can be made to capture, as I said, also the solutions corresponding to, for example, in this case, generated by, generated by these 3 points. So that will give us a D-module, which corresponds exactly to the image of the source category in the spherical functor, and that sort of gives, as I said, a way of doing the, trying to understand the how these strata interact. So in this example, although the details are not very pleasant, but I think that I checked most of them. Modulo some facts about the BBGKZ. It's still interesting to understand this perhaps just abstractly at the categorical level, and of course to try to make sense of this, what it means at the level of the associated in the mirror picture of the Fukaya story, which I haven't thought about. So sorry, and I apologize for going over time. So thank you.